In this video, I'd like to talk about the math question of the day for Friday, May 5th, 2023. And with this problem, we need to solve the equation, which is an exponential equation. We have 4 raised to the x minus 2 is equal to 5 raised to the 3x plus 2. And we just need to figure out which x value would make this equation true. And questions like these will typically show up in either in Algebra 2 class, maybe towards the end, or in a pre-calculus class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And with exponential equations, there are several strategies. One is that if you can rewrite both of these bases as the same base, then you can just equate the exponents. So for instance, if this was 8 raised to the 3x plus 2, then we could rewrite 8 as 2 cubed and then use exponent properties. We could rewrite this as 2 squared. And again, we'll just use exponent properties. We will essentially just distribute the 2 to each. We distribute the 3 to each of these, since an exponent to an exponent is multiplication. And then it would be 2 to something is equal to 2 to something else. And for this to be true, A would have to be equal to B. And that strategy will work if we can rewrite these bases as the same base, as some power of the same number. However, 4 and 5 cannot be written as the power of the same number. So this strategy will not work here. And if this strategy doesn't work, what we can try is using logarithms to solve our equation. For instance, if we have, let's say, c is equal to d, something equal to something else, then it's also true that the log base a of c is equal to log base a of d. As long as they have the same base here, then the inputs of these logarithms must also be equal. So in effect, we can take a logarithm of each side, or we can think of these as the inputs of the same logarithm. And we can choose whatever base we want. We can use maybe base 10, since that's the common log, and we have a button for that on the calculator. Or we can use maybe the natural log, which, remember, is just log base e of some input b. This is usually written as ln of b. This is the natural log of b. And like I mentioned, either one you want to use. Let's say we have log base 10 of, I already used d, let's use some other letter, f. This is usually just written as log f. And I focus on these two specific bases, e and 10. Remember, e is just that irrational number, 2.718, and so on. It is infinitely long in its decimal expansion. These two bases are most common, for one, because we use 10 as the basis of our entire number system. And e, it's a little bit more complicated, but e has many very special properties, especially when you're dealing with calculus. So we call this the natural log. These bases will generally show up on most graphing calculators. But if you have more advanced calculators, then you can really just plug in whatever base you want as a button there. So you can choose any base you want. That's up to you to decide, but typically these are the ones most commonly used. So let's use the natural log here. We will put these two sides of the equation as inputs of natural logs. We'll have the natural log of 4 to the x minus 2, and this is equal to the natural log of 5 to the 3x plus 2. And like I mentioned, we are, in some sense, just taking a natural log of both sides of the equation. But from here, we can use logarithm properties to rewrite our equation. Since we know that if, let's say, we have the natural log of x raised to the y power, we can bring the y down in front so that we are multiplying y by the natural log of x. And these are equivalent to each other. This is one of the most important properties of logarithms. And in this case, we have exponents for both of these, and we will bring those down in front so that we're multiplying. We have x minus 2 multiplied by the natural log of 4, and this is equal to 3x plus 2 multiplied by the natural log of 5. And keep in mind that the natural log of 4 and the natural log of 5, those are both just numbers. You can plug those into the calculator and see what their decimal expansions will be, but they are irrational numbers, so they will have infinitely long decimals, though your calculator will approximate it. So at this point, we can distribute these logarithms to each of these. We would have the natural log of 4 multiplied by x minus 2 times by the natural log of 4. And this is equal to the natural log of 5 distributed to both. We have 3x multiplied by the natural log of 5 plus 2 times by the natural log of 5. And if we want to simplify terms like these, we can combine the 3 into this. We can essentially use this property in reverse, put the 2 back on the inside, and it would become 4 squared, and rewrite that as the natural log of 16. That is a preference if you prefer to maybe clean it up a little bit, but let's do that just for some extra practice. We would have x multiplied by the natural log of 4 minus the natural log of 16 now. We could bring this 3 on the inside so that we have x multiplied by the natural log of 5 cubed, or 125. And we can bring the 2 on the inside. That will give us the natural log of 25 since we are squaring 5. And to solve this equation, we have the variables on both sides. So let's move them to the same side of the equation. We can subtract, let's say, this value here. It doesn't really matter. We can subtract both of them if we want, or I should say either of them if we want. And we're subtracting x times by the natural log of 125 on both sides, so that on our left-hand side, we get x multiplied by the natural log of 4 minus x times by the natural log of 125. And I will also add the natural log of 16 to both sides so that we can get all of the x's on one side and all of our numbers on the other side. So that now we have the natural log of 25 plus the natural log of 16 on our right-hand side, since this will cancel out. And let me just make some more room so that we can keep working here. Now from here we have x in both of these terms, so we can factor that out so that we get the natural log of 4 minus the natural log of 125 in parentheses. And over here we could use another logarithm property if we want to combine this into one term. If, let's say, we have the natural log of, let's say, capital G plus the natural log of capital H, if we have a sum, we can combine these to one logarithm as long as they have the same base, where we are multiplying these as inputs. So this can be rewritten as the natural log of 25 times by 16. And now we just have one logarithm here. And likewise, if we're subtracting, let's say we have the natural log of g minus the natural log of h, then this would be a quotient on the inside, g over whatever we're subtracting, or the input of what we're subtracting, which would be h. So we can rewrite this as well. This would just become x multiplied by the natural log of 4 over 125, and this is equal to this product here, which would just be 400. So we have the natural log of 400 there. And lastly, we can divide both sides by this factor here, this natural log of 4 over 125, to cancel out this multiplication. So let's quickly do that. And we need to do it to both sides. But this will isolate x, so that x is now equal to the natural log of 400 divided by the natural log of 4 over 125. And this should be our final answer, though if we want, we can also find the decimal approximation to this. And using the calculator, we can see this is approximately minus 1.7406, or we can just say minus 1.74. But again, this is irrational, so it will technically have an infinitely long decimal expansion. And if we do want to see if we are technically correct here, we would need to plug that back into the equation and make sure we get something that actually makes sense. And since we're approximating with our decimal here, we would get something that is approximately true, but it should be pretty close depending how much you round your x value by. And I will leave that as an exercise to the viewer, but if you do plug in that x value we find to both sides of this equation, it will simplify to the same number on both sides.